Sedimentary basins are fundamental structures of the outer part of our planet, and they're important structures for hosting critical resources such as hydrocarbons, water and minerals, and they're tape recorders for Earth history and of tectonic processes happening within the Earth. In this introductory presentation, we'll be looking at a series of tectonic concepts. We'll look at the ways in which sedimentary successions load plates and how they may accumulate within inherited holes. But much of what we'll look at is how holes, basins themselves, may be formed tectonically through the processes of plate bending, so-called flexure, and by pulling plates apart through extensional tectonics. And we'll also look at a rather surprising type of process as well. But more of that later. Let's look at this view, which is looking down on the Tarim Basin, and we can see the big large area in the middle of the image here, which is where sediment is ponding, and it's being delivered from a series of mountain ranges around the edges. And if you look closer, you can see the delivery system through river systems. So that's a sedimentary basin, at least one on land, where we can see the scale and we can see the types of geology we need to consider in considering the whole of the basin. But what's it doing there? Why does the sediment accumulate? Well, let's conduct some rather simple experiments based on Archimedes. So let's consider a continental plate. It's got a crust with the density labelled there, and that rests on upper mantle, and at some depth that upper mantle will behave like a viscous fluid, so it will deform if you put loads on top of the plate. So let's do that. Let's put some sediment on top. Here's some sediment, and sediment has this range of densities. Significantly lighter than not only the crust, but more critically, of the upper mantle at depth. So the geometry we see here is not sensible. What we need to do is let this subside. So the sediment has loaded the plate, and consequently the plate subsided. And the geometry we're looking at here assumes a very simple case that the plate has no strength. So the load is not transmitted laterally, the sediment just subsides directly under itself. And the mantle at depth flows away. Now what Archimedes demonstrated was that the load displaces an equal mass of the fluid upon which it's floating, in this case the upper mantle. But because the upper mantle has a higher density than the sediment, the volume of upper mantle that is displaced is less than the amount of sediment. Therefore, our sediment load pokes out at the top. So this is a really important point. The mantle at depth has a higher density, therefore takes up less volume than the sediment load that's imposed upon the top of the plate. So there's less subsidence of our sediment column than the height of this column itself. This is what happens if we put more sediment on top. Okay, the sediment loads the plate and subsides. But again, it displaces a lower volume of mantle at depth because that mantle is denser. So the more load we add, the higher it rides on our plate. Now this clearly is going to create a problem because it means that surface processes will act upon it and flush that load away. So the implication is that in our simple world, we can't accumulate a sediment thickness. So the message is we need to make a hole in some way or inherit one. Well, let's go back to the Tarim. There's clearly some sediment there, but how thick is it? So here's a sediment thickness map for the area, and you can see that thicknesses exceed 9 kilometres in the deeper parts of the basin. But throughout, there's many kilometres of strata deposited. So how is it that this pile of sediment has not been flushed away? Well, the fact is it's contained behind high walls, these main mountain ranges of Asia. Let's just take our sediment map away. And you can see them really clearly in the satellite image. So the Tarim Basin is able to accumulate thick sediment piles because it's contained behind high walls of mountains. Let's zoom out again. So here we are looking, you can just about see the Tarim before it disappears over the horizon. There, a landlocked basin. But not all basins in this part of Asia are landlocked by any means. Let's look to the centre of this image here, in the south of the Himalayas, where there are clear river systems associated with the Ganges that are flushing sediment away from the mountains and down to the Bengal Fan. So this system is clearly not contained. So we can zoom out and look at the system in here, and here's a map of sediment thickness. And the sediment thicknesses in here in the Bengal Fan achieve thicknesses of over 20 kilometres. This is an inherited hole. The sediment is ponding on top of oceanic crust that's 120, 140 million years old. The sediment's obviously happening today and through the past several tens of millions of years. So we have an inherited hole along the southern edge of the Asian continent into which sediment is being poured. And we can see this is a really important process generally around the margins of the world's continents. The world's thickest accumulations of sediment are on the shelves or beneath the shelves and on mega fans where the world's major river systems reach the oceans. So let's look at the effects of that sediment load on the underlying plate here in the Indus Fan. This is a geological section. Notice the scale. The vertical scale there's 10 kilometres, the horizontal 100, so there's significant vertical exaggeration here. And this diagram was created from a regional compilation of seismic profiles. This is the same image but vertically exaggerated just to make this clearer, and you can see that the underlying Cretaceous strata and the oceanic and margin of the continental crust have been subsided down beneath that thick mass of over 10 kilometres of tertiary strata. So sediment is loading the lithosphere, which actually creates more available space for sediment to pile in. So the sediment can build up considerable thicknesses, provided that we start off with a hole, in this case provided by the bathymetry above oceanic crust. So this inheritance of a basin through the formation of oceanic lithosphere is why we're able to accumulate thick sedimentary piles around the margins of the continents. So let's just return to this part of Asia. We've seen that we've got the landlocked Tarim Basin and we've got the two major depot centres flushing out through here into the Indus and the Bengal Fans on either side of the Indian subcontinent. In the Tarim case, we've ponded our basin behind mountain ranges. In the case of the big fans, we have inherited holes, the bathymetry of the floor of the Indian Ocean. But not all the sediment is either ponded in the Tarim or flushed out to the oceans. There are sedimentary basins formed on the continent. So let's look at these processes. The processes of making holes, places to accumulate sediment actively through tectonics. And we'll look at two key processes: bending plates and stretching plates. And we'll start off with the first of these, flexure. So let's look at this area here on the southern flank of the Himalayas. Here is a sediment thickness map compiled for this area. And let's just zoom this in. So on the southern flank of the Himalayas, there are sediment accumulations that reach thicknesses in excess of 6 or 7 kilometres. And you can see that the sediment thicknesses, rather curiously perhaps, are greatest as we approach the Himalayas. In fact, that's a systematic pattern, isn't it? As you go from the Indian Craton towards the Himalayas, the sediment thickness generally increases. Well, to think about what's going on, we're going to leave the Himalayas and go to the oceans. So here we are in the middle of the Pacific, and this is the Hawaiian archipelago with the islands in green and the eroded margins of these islands shown with the shallow water in those reds and pinks. And then surrounding this island chain is a moat of deeper water, shown by these dark blues, before you return to more normal values moving further away from the islands. Why is this? Well, let's just consider this on a profile. And the idea is that the crust of the Hawaiian chain is thick. This is a chain of volcanoes. And these volcanoes have loaded the lithosphere upon which they've erupted. these volcanoes are supported across a wide lithospheric region. So consequently, the surrounding lithosphere has subsided, and that part that is not containing volcano remains as a moat of deeper water, bending or flexure of the oceanic plate. So let's take this idea and return to Asia. This process of loading adjacent to mountain ranges creates a foreland basin, otherwise known as a foredeep. Let's zoom in. So here is this foredeep basin with the Himalayas forming the snowy hills on the right and the Indian Craton over there on the left, and the basin in the middle in the lighter green colours. And you can see the Ganges and associated river systems flowing towards us across the image. So let's think about this in cross-section. And what's happening here is the lithosphere of the Indian continent is going down under the Himalayas, and as it approaches the Himalayas, is flexing downwards, rather like a springboard. So this is a foreland basin. It's forming because of flexure of the Indian plate by the advancing mountain range, and the shape of this deflection depends not only, of course, on the location and magnitude of the load, but also the strength of the loaded plate, along with whether this basin is filled with sediment or water. As we've already seen, sediment itself acts to load and deform the plate. Well, it's not only continental plates that are deformed by these types of mechanisms. Oceanic trenches are a dramatic illustration of bending plates, bending through subduction, and they create a series of basins in the forearcs, ahead of the volcanic arcs, in other words, associated with these subduction zones. Let's just look at a classic one here on this part of the Japanese archipelago, a place called the Nankai Trough. This area has been studied not least, of course, because these subduction zones along the margins of the Japanese archipelago generate megathrust earthquakes and associated tsunamis. So understanding what's going on in these places has a huge impact on evaluating geological hazards in the region. And as a consequence, some spectacular imagery is being created, not only this bathymetric map that you can see for part of the Nankai Trough, but also some seismic profiles. So here's an interpretation of a seismic profile through here, with Japan would be on the left-hand side of this image and the Philippine Sea on the right. Philippine Sea plate subducting northwards beneath Japan. And as a consequence of that displacement, sediment on the floor of the Philippine Sea is being scraped off into a so-called accretionary prism. Here's a better version of this seismic imagery, and you can see rather spectacularly the stacking of the strata as the Philippine Sea plate is subducted. So off-scraped sediment creating an accretionary prism. So much of the trench, indeed pretty much all the trench of the Nankai, is filled with tectonically stacked sediment, the accretionary prism. And the same is true for foredeep basins as occur on the margins of the Himalayas. The place where the basin is existing is only a residual part of the overall flexure, because much of the foreland basin is filled with stacked strata as the Himalayas continue to advance southwards onto the Indian Craton. Clearly, understanding depositional systems in these settings requires also unravelling the thrust structures which have stacked up the margins of the basin. Okay, so let's leave these types of flexural basins alone for a while and look at a second way in which we can create holes. And this is through rifting. And probably one of the clearest places to understand these sorts of processes is here on the margins of the Red Sea. The Red Sea, of course, is forming as a consequence of the stretching between the African continent on the left-hand side of this image and the Arabian continent on the right. Well, let's look at the northern part of this, the Gulf of Suez up here, and understand what's going on through this process. So let's look at a couple of cross-sections through here. So here in the north, we can see a series of normal faults that have stretched the upper crust, pulling the strata that were there before rifting, the so-called pre-rift strata, apart and creating new sedimentary basins and a sedimentary fill shown in the blue there above these normal fault systems. We can compare this section in the north with one further down the Gulf, and as we go down the Gulf, the amount of normal faulting has increased, and the width of our basin, shown by the blue strata, has increased as well. So more stretching as you go southwards towards the Red Sea. Interestingly, the width of the water in the Gulf of Suez is significantly less than the area that the stretchings occurred over. So this is the area of the modern sea through here. So the basin width that you see at the surface today is not necessarily a reflection of the total width over which that stretching has occurred. The modern basin is rather narrow, and stretching continues. Well, there are other places in the region down here where there are sedimentary basins forming because of rifting processes. And a little chain of these lies associated with the Dead Sea. Well, that region there is forming as Arabia is moving northwards and colliding with the Eurasian landmass to form those mountain ranges through the Zagros, toward just north of the tip of the arrow there. And that northward movement is happening, but in the eastern Mediterranean it isn't. So what we have between the two areas is a plate boundary with this sense of movement on it. It's a strike-slip zone or a continental transform, and within this region in here, sedimentary basins are opening up. We can look at that area here on the southern part of the Dead Sea system, so the water body on the bottom of that's the Gulf of Aqaba, and the Dead Sea is just off the top of the image there. And you can see because of that sense of strike-slip movement through the region, there's local stretching between fault blocks, creating a chain of linked small sedimentary basins. So strike-slip systems also have basins on them. The basins don't have to be pulled apart by movement perpendicular to their trend. So let's leave this area between Africa and Arabia and move up here to the margins of northwest Europe and the Viking Graben. Much of our understanding of sedimentary basins comes from this area here, associated with hydrocarbon exploration, particularly through the 1970s and 80s. So here's a regional seismic profile collected through this basin area of the Viking Graben, the northern North Sea, between Norway on the right and the Shetland platform towards the left-hand side and out into the Atlantic if you were to go further to the left. This is a series of deep seismic reflection profiles acquired to image the crustal thickness and to explore mechanisms of basin formation. And this one was acquired in the early part of the 1980s. Let's just add some colour, and you can see the idea that the crust under the Viking Graben is thinner than the margins under the Shetland platform and critically beneath the Horda platform and as you move towards Norway. So we're looking at evidence here of crustal thinning, presumably formed by lithospheric extension, and the Viking Graben, the sedimentary basin, deformed in this zone of crustal thinning. In this image, the faults are not shown, it's just a simple idea of crustal thickness variation. And so, intracontinental rifts are important areas for accumulating thick sedimentary successions, and obviously contain important earth resources. And the interesting question is, can you move from these intracontinental rifts to wholesale rifted margins and the formation of new oceanic lithosphere? Are the processes the same? So this section here, again based on seismic from offshore Iberia, shows an array of normal faults and thin continental crust as you go off towards the left into the Atlantic. So a key question is, do intracontinental rifts simply evolve into rifted continental margins by the same type of stretching? And consequently, can you make predictions about where the resources are within these more extended parts of the continents? So let's return to the continental interiors, where there's a class of basin, so-called Chrotonic basins, which are rather harder to explain through conventional tectonic processes. Take the Congo Basin here. It's a huge area and contains sediment thicknesses in excess of 10 kilometres. And unlike the rift basins, and indeed the fallen basins we looked at, it's not a linear feature at all. The characteristics of cratonic basins, like the Congo, are for this sort of bullseye pattern of concentric isopachs. So they have a quasi-circular plan. And when you look at sections through them, have little internal faulting, and they have a history that suggests that the subsidence rate wanes through time. The lack of faulting indicates that these basins do not form by the margins of the basins moving relative to one another, at least laterally. So let's think about another mechanism. Let's go back to our simple cartoon of a plate and think about what would happen if we change the mantle density. So if we put dense upper mantle in here, or denser lower crust, that will drive subsidence. So if those patches of upper mantle anomaly are point sources rather than linear, the resultant basin will be quasi-circular in plan view. These basins have been enigmatic simply because in order to understand them, if these ideas are correct, we have to understand about the dynamics of the mantle. These rather enigmatic basins are actually rather common, and they're found on the cratons that occur in the interiors of pretty much all the continents on Earth. Examples in North America are the Michigan and Williston basins, and in South America the Parnaíba basin. So that's a brief introduction to sedimentary basins and the tectonic concepts that underlie their understanding. We've seen that sedimentary successions load the lithosphere and can build up to thicknesses, well, up to 20 plus kilometres. We've seen that this happens chiefly at the margins of continents where holes are essentially inherited from the formation of oceanic lithosphere. The dynamic formation of sedimentary basins can involve the bending of plates through flexure adjacent to imposed loads, particularly mountain ranges. And we've also seen that basins can form by extension where the lithosphere has been stretched. These tectonic processes involve not only the shallow crust upon which the sediment has been accumulated, but also the whole of the plate. So understanding these processes involves understanding how the deep earth works. And this is particularly true for the Chrotonic basins, which may be explained perhaps entirely by processes that are acting in the upper mantle. Understanding sedimentary basins, then, is a multidisciplinary activity.